Now we can make a seashell shape, because we can generate one of these helicospirals, and now I can hang off that spiral, a semicircle, and rotate that round with it. Okay? So there's my helicospiral. I'm going to imagine pinning this shape to the end of the curve and rotating this around. Okay? So you're pretty good at telling me where I am on the spiral, okay, in terms of theta, but now I ask, where am I in terms of the seashell surface? You'd need to tell me where I am on the generating curve. So you'd have to sort of move yourself around this curve and then add on a little bit to work out how far you've moved away from that curve. Okay? So I can tell you where you are on the seashell surface, not in terms of one number, theta, but in terms of two. Theta tells you where you are on the curve, and phi tells you where you are on the opening, the generating shape. Okay? So if I ask you, what's this point here? Okay? Well, it's a little bit removed from the helicospiral by an amount proportional to, it's something to do with this radius and this angle. Okay? If you do a little bit of geometry, you can work out that the distance from the center line onto the seashell surface is nothing more than the distance onto the helical curve plus a little bit more, r sine phi. Okay? Likewise, if I want to ask you how far you are from the origin up here in the z direction, a little bit of algebra, a little bit of trig rather, geometry tells you where you are. Do you have a question? Yeah. It does, okay? So theta, I've called it an angle. You can think about it keeping going round and round and round and round, okay? Whereas this angle here this is a proper angle, okay? Because I won't let it get more than a semicircle big. So in terms of 3D Cartesian system, the coordinates of the shell are given by x, y, and z, but now x, y, and z are given in terms of r cos theta, r sine theta, and z. Okay? I'm using the planar system to tell me where I'm in the plane, and z to tell me how far I've moved away from the plane. Okay? But what that really does is allow me to specify the seashell shape in terms of this angle theta and this angle phi. We parameterize the surface in terms of two numbers. Okay? And I've written out explicitly what they are here for this Archimedean spiral. Okay? But it just says if you want to work out the x value of where you are on the seashell, okay, you work out your distance from the helicospiral. The helicospiral was Archimedean, so the distance there just goes as theta. You add on the bit to get you onto the semicircular opening, okay? And then you project that onto cos of theta, because x is r cos theta. Okay? And we get three formulas that involve theta and phi. Okay? So this is an in-principle argument. I don't really want you to worry about the details, but if you follow this through and use these equations to parameterize a shape in your favorite mathematical software for plotting pictures, then you can make shapes like this. Okay? So you can see here, there's my semicircular opening, and I've rotated it around a nice, simple helicospiral. Okay? So that looks a little bit like a seashell. And you can play these games now where you start changing the shape of these openings, changing your choice of helicospiral, and you see if you can match up the pictures from your maths with pictures from the natural sciences. Okay? So to make more interesting spiral shapes, we just play with more interesting curves. Okay? It's as easy as that. Here's what happens if we let the semicircle expand as it's rotated. Okay? So last time the semicircular shape, the opening did not change, and now I can let it get bigger as theta gets bigger. Okay? So I'm going to let its radius increase linearly with the angle. Okay? And you make a nice shape like this. The opening's bigger as the animal gets older, in some sense. Here's one with more of an ellipsoidal shape. How did I make it? Okay? Well, I just changed one of the curves I use. Okay? Here's one with a more elliptical opening. How did I make it? Well, I rotated an ellipse around my helical spiral. Okay? So how many different shapes can you make with this sort of idea? Well, lots and lots and lots and lots. Okay? So here's what I've called my little zoo of mathematical seashells. Okay? So these are not real seashells. They are little pictures I plotted. Here's Lyria, here's Epitonium, here's Turritella, here's Conus, Planorbis. They've all got nice names, okay? But these look like the ones that you would see down at the seaside. So how do I plot these? Well, in some sense, it's more than having the equations. I need some software, some computer, some CGI to help me animate these or at least render them. Now, there are many mathematical packages out there. Mathematica, MATLAB, Maple. You may have come across some of these. To plot some of the earlier figures in my talk, I used something called Mathematica. Okay? But these packages are not free. They're expensive. You have to cough out hundreds of pounds for them. So there's a programming language called Python, which is free. It runs on all platforms, Windows, Mac, Linux, Unix, you name it, okay? And this is my code I use to write, to plot those shapes for you, okay? It's not important what the code is. It fits on the page. But the nice thing is it's free, and it is really named after Monty Python and his Flying Circus, okay? So people that use Python like puns, okay? So you see, if you've got good eyesight, you see some of my variable names in my code are called things like spam, okay? So if anybody wants this code, I will make it available. You can plot these shapes yourselves. If you have access to the code, then you can play around not with just the static images, but you can grab one of the images that the Python code generates, and you can sort of drag it around. And okay, you can rotate it and look at these shells from all different angles. Okay, so you can clearly see the opening here that I've chosen is nothing like a semicircle anymore. Okay, but you can definitely see something helicospiral here. And I've got bumps growing on the shell lip and so forth. Okay, so I've made the shape a little bit more complicated than it was in my talk.